4th Lemke or 5th, something like that. You all right, Jeff?
Yeah. He's trying to keep presenting this. You're not helping, Jeff.
All right, thanks everybody for coming. I am going to be going over a bunch of things today that I think you guys have been interested in, will find very interesting. Our safety certifications like UL and CE, what they are, what they're for, what EMI is, what the safety tests that we do, what specifically they are and we're testing for, our efficiency certification, which we call DLC, what color temperature and CRI are, and then we're going to get super nerdy and we're going to talk about the wave particle duality of light and thin film interference, which are near and dear to my heart because I'm a super nerdy engineer. So our safety certifications, the big one that we do here is UL, which is the Underwriters Laboratory. It was a not-for-profit testing organization that came up with standards to make sure that all sorts of products were safe. Last year they became for-profit, so we're gonna see what that changes to how we interact with them. But for our purposes, this is the US, Canada, Mexico. It covers a lot of the Western Hemisphere. We send our products out to get tested and verified that they're safe to their standards. Now CE is for Europe. It's a short for a French word for their organization. That's the safety organization for the European Union. They set the standards for Europe, and then what you'll find is a lot of Europe, Asia, and Africa follow their certifications. They're not one for one, so just because you're UL doesn't mean you're CE. Just because you're CE doesn't mean you're UL. Getting both is usually a little bit more expensive, quite a bit more expensive actually. Now we also do NAM, some of our products, which is the Mexican safety organization. Some of our products need to get NAM certified. And then you also are probably all super big fans of SASO, which is the Saudi Arabian safety organization, which is probably the hardest for us because, as Matt knows, we have to certify every single time we ship anything to Saudi Arabia, we have to get it recertified. So they're very, very stringent on their requirements. So the other thing that we deal with, this is the only thing that the federal government holds us accountable to, and this is electromagnetic interference. Some of you guys were around when my monitor went bad. Every morning I'd come in and I'd turn it on and everybody's radio would just start screaming static. That's EMI. So it's just stuff coming out of cell phones or speakers. It's just blasting out all this signal, and cell phones or radios or TVs can pick it up, and then you just get static all over the place. So the Federal Communications Commission in the US is the one that holds us accountable. This is a pretty big deal because what'll happen, and what has happened in the past, is products that we, not in this facility, but the company has made, have been bad, and it interferes with other big companies' equipment, and they come and find you, and then they tell the FCC, and then you get in big trouble. So it's really hard to hide because you're sending signal out all over the place, and it's really easy for other people to find you when you're violating those rules. In Europe, it's called CISPR 15, which is their really long word for their safety certification for EMI. Their standards are much more stringent than the US's standards are. So the US is FCC, and then Europe is regulated to CISPR 15. Oh. So you'll have to stay with me. This is the dry portion of my presentation. So the one test that we do is HIPOT. So it's short for the dielectric voltage withstand test, which is what we do is we apply a really high voltage to the fixture. We're attempting to get the insulation or some component to fail and then send current through the fixture. And we use an Associated Research test device, and it'll detect the current flowing. We are really good about it now. We have had products that other people have sent us, and products here that when they fail, you can see the arc. You'll hear it and see it, the failure. Now, we also do ground continuity checks. So that is making sure that the fixture is safe in case something somewhere breaks, something goes dramatically wrong. We're giving electricity a safer path to travel to ground other than a person. So that's what all the green wires we put in are. They actually connect to the earth so that if there's a problem, instead of flowing through a person, it'll go to ground. I did want to read you this extremely exciting, this stuff, if you read UL's 1598 standard, edge of your seat reading. Are you ready for this? The dielectric voltage withstand test apparatus shall include a 40 to 70 hertz transformer having an essentially sinusoidal output with a rating sufficient to maintain the required test potential. So imagine thousands of pages of reading stuff like that. It's not the most exciting stuff to read, but we do have to make sure that we comply with it. Now the other certification that you may hear us talk about, probably you guys less so, technology talks a lot about it a lot, and that's DLC, the Design Lights Consortium. It's an organization governed by the Department of Energy, but the lighting industry got together and said, we need to have standards so that everybody's speaking the same language and we're holding each other accountable. So if we say this fixture is 90% efficient or attains a certain lumens per watt, somebody's testing it and making sure that they're not lying, because power utilities and municipalities give rebates to our customers. So they'll buy a fixture and they get money back from the utility for buying our fixture because it reduces demand on the power plants. And so they want to know, did you buy something that's okayed by DLC? Because if you did, then we're going to give you a big cash check for buying this and reducing demand on the grid. What we use in order to determine that is an integrating sphere. If you guys haven't seen ours, we have a 6-foot huge sphere. You put the light in there, you turn it on, you leave it for like an hour, and it measures the total light output of the fixture and the total energy consumption, and it can also measure CRI and color temperature to tell you exactly what that fixture is putting out in terms of light quality. Now, CRI is the color rendering index. This is a value measured between 0 and 100, and it measures how closely artificial light matches light from the sun. In reality, well, if you ask a physicist, it's how close it matches black body radiation. For our purposes, think of how close it matches the sun. Color temperature, this is how warm the light looks. So 2700 at the low end is a very yellowish red light. It makes your skin look very soft. If you come up to 5000, the light looks really, really blue. People don't look very good at 5000 Kelvin, but usually you're more efficient up here. So the development of LEDs, if we go back to the history of this, the first working LED was developed at GE in 1962. Now, the big breakthrough for using LEDs for light happened in the 90s. 3 guys from Japan developed a blue LED, which was critical. They won a Nobel Prize in 2014 for that achievement because it was so important. And the reason it was important is, if you look at the LED, there's this yellow stuff over it. This is phosphor. It's technically a phosphor silicone blend. When the blue light hits that phosphor, the whole spectrum shifts and we're into something that approximates sunlight instead of being, without it, I don't know if you guys have ever seen it, if somebody knocks that yellow off, it's just incredibly blue, just awful color. So that's what the importance of both the phosphor and the development of the blue LED. So this red line, this is, let me go back. The left part of this graph is radiation intensity. This is energy coming out of the sun. So if you look at this red line, this is the sun. So here's infrared, ultraviolet. If you look, the reason why we all see invisible light is because visible light is the most intense thing coming out of the sun. It's no accident that we see visible light instead of some animals which can detect infrared, or insects which see ultraviolet. Now, if you're looking at CRI, you can see this is what sunlight looks like in terms of what each color and their intensity compared to LEDs, which is reasonably close, although a little bit blue way over here, and then it kind of smooths out as you get red. Incandescent lights are a huge slope, and then CFLs, this is why nobody likes CFLs, because this here looks nothing at all like the sun. It's not even close. That's why things don't look right. Now, this is where we're getting really nerdy. I'm gonna try my best to explain this. I'm not sure that I can do it justice, but for 400 years, some of the best, brightest physicists in history were trying to figure out if light was a wave or a particle. So I want to give some perspective on how good each of these, well, some of these guys were. So Einstein, if you guys didn't know, developed calculus in about I think a 5-year time span at Oxford. By himself, after developing calculus, he was able to take a telescope and a stopwatch, and he could tell you the mass of any planet in the solar system. It's all he needed to tell you the mass of the Earth, the Sun, Jupiter, Mars, everything, which is pretty incredible. Fresnel developed a lens used in every single lighthouse in the entire world that basically allows ships to navigate, because he was able to figure out how to chop lenses down and make them thin, because you couldn't cast giant 20, 30-foot lenses that were 5 feet thick. Glass just couldn't handle it. Maxwell developed all the equations that govern electromagnetics, so electricity and magnetism. He has, I think, 4 really famous equations. The urban legend around how good Maxwell was goes like this. Maxwell walked into class late one day. There was an equation written on the blackboard. He's copied it down, thought, oh, here's my homework. Goes home, solves the problem, turns it in, and his professor's like, this was one of the unsolved problems of mathematics. I can't even believe it. Now, not quite that impressive. It was a proof that only one other person had ever been able to prove. Maxwell worked through it as what he thought was a homework problem. Accidentally, didn't even know. So they fought over this for a long time, and what they discovered eventually is that it exhibits properties of both. So if you think about waves, with the experiment they did, which is they cut 2 slits in basically a wall, and they shined light straight at it. And what happens is you see these areas of dark and light, and you're like, oh, well, the waves are interfering with one another, and they're creating these light and dark spots. That makes total sense. But what you find is that light has, the smallest unit of light is called a photon. What you could do is you could shoot a photon at the same 2 slits, and you know what happens? You shoot it through once, and it winds up to the left. And the second time you shoot it, it winds up to the right. And if you shoot enough of them, you get this pattern that looks like the waves. And so what they find is that, oh, well, shooting it through here, this is really hard to explain, but you can't reliably shoot it through the 2 slits and tell where it's going to end up because of the properties that light exhibits. For me, this is probably one of the coolest, although topics I don't fully understand, but I think it's pretty sweet that people were able to figure this out. Now, the last part that I really also enjoy is, for a long time, I wanted to know why you get a rainbow on oil spills, oil slicks, right? Well, it's because light acts like a wave. So what you find is, this is the oil slick. It's a thin film. Two waves of light are coming in parallel to one another. One of them reflects off the surface of the oil. The other one reflects off the surface of the water. And what ends up happening is you get destructive interference. It cancels out one of the colors of the rainbow. So the colors that are in here are magenta, cyan, and yellow, because they're missing either green, blue, or red. So that's what you're seeing here, is that one of the colors of the rainbow is getting canceled out in that thin film. Now, the application that we have is, this is how they make anti-reflective coatings on camera lenses or your cell phone screen. Put a thin film over it so that when light would reflect off of it, they can set it up so that it cancels out the reflection. So that was everything that I had. I hope that you guys thought it was really interesting. And thank you very much for coming.
Yeah.